Alright, welcome to Chem 120 Fundamental Chemistry at SUNY Broome Community College. I'm your instructor, Dr. Daniel Brennan, and this is the first of many audio narrations of our slideshows. You also have the slides available in the various chapter folders in your Blackboard course. So the way I would suggest that you use this is treat this like a traditional lecture. Obviously, it's not quite as interactive, but I do encourage you to ask questions, send emails. If you're in the area, my office hours are Fridays from 11 to 1, and I would love to see you then so that we could work problems. But if you're not in the area or that time's not convenient and you can't make a convenient appointment, then I would recommend sending emails, and we'll do the best we can do answering questions and corresponding by email. Alright, so in this first chapter of the course, we have a number of learning objectives or learning outcomes for you. We'll be able to define science, chemistry, technology, and alchemy as one of our learning outcomes. We'll also be able to describe the importance of green chemistry and sustainable chemistry, which should be the goal of all of us as chemists or individuals who've had some college chemistry. We'll define a hypothesis, scientific law, scientific theory, and scientific model, and explain their relationships in science. Again, these are things you've probably done at an earlier level, although maybe not in a way that seemed meaningful then or is particularly memorable now. Hopefully we'll change all that. And then finally we'll define risk and benefit and give an example of each. These are the objectives for this page, but we have a number of others, as you'll see as we go forward. Moving right along, we see we'll also be able to estimate a desirability quotient from benefit and risk data, distinguish basic research from applied research, differentiate mass and weight, physical and chemical change, and physical and chemical properties, classify matter according to state and as mixture, substance, compound, and or element, assign proper units of measurement to observations and manipulate units and conversions, calculate the density, mass, or volume of an object given the other two quantities, distinguish between heat and temperature, two related although distinct terms, and then explain how the temperature scales are related. And finally, we'll use critical thinking to evaluate claims and statements. We'll define green chemistry and then describe how green chemistry reduces risk and prevents environmental problems. So as you can see, we have a lot of objectives and a lot of work to do in this first chapter and throughout the rest of the course. So let's get to it. So chemistry is the study of matter and its changes. That's where we fit into the realm of science. Again, science will also define that's a particular way of studying the world, but chemistry should be at least everyone's favorite science because everything we do involves chemistry. I know a lot of you are in this course for a variety of reasons that probably don't have a long-range goal of becoming chemists as professionals, but certainly professions that use chemistry, dental hygiene, or other health professions, or maybe biology or other natural sciences. But again, all of these make great use of chemistry. So even the non-chemist really has to have at least a fundamental understanding of what chemistry is and why it's so important to everything we do. So let's take a step back now and define science, a broader term. Chemistry is one of the natural sciences, but science itself, as our text defines it, is the process of seeking an understanding of the underlying principles of nature. It involves two facets, technological or factual, and philosophical or theoretical. Really, science is based on logical argument of empirical data, meaning that things that can be tested in the lab. Depending on the science, maybe astronomy is more of a modeling type thing since we can't really get out in space and test everything. But for chemistry, we tend to be thinking of experiments or at least computer simulations that allow us to visualize matter, visualize those atoms and what's going on. And the last component of science is skeptical review. So if you do something in the lab, you have some empirical data, and it fits together into a logical argument, again, that's great, but you need to put it out there and let your fellow scientists critically examine it, decide if it really passes the tests of being acceptable, or whether you may have put things together in a way that seemed logical to you, but really doesn't fit everything else that's out there. So again, a little broader than what our text goes into, but those are the hallmarks of science: empirical data, logical argument, and skeptical review. And in particular in chemistry, obviously that will involve matter and energy and the changes that matter undergoes. So we have some more definitional terms here. Technology is the direct application of knowledge to solve problems. We have science coming out of this natural philosophy, or the philosophical speculation about nature. Humans have been interested in nature pretty well as long as humans have been a separate species. We're very curious, and that natural curiosity is good. Unfortunately, most of you lost it sometime during your middle school years, probably. I've taught in a number of levels, and elementary students are fascinated by everything. They're very eager and excited, and they want to know more about the natural world. By the time middle school happens, there are other interests, and then by high school, we've pretty well killed that curiosity. So hopefully here now in college, whether you're 18 or 80, we can rekindle that love for understanding more about our natural world. Chemistry in particular is the discipline of science that deals with the behavior of matter. Again, physics also deals with the behavior of matter. The big difference between chemistry and physics is chemistry is the science of change. We're looking at how that matter changes in our particular area through the course of a chemical reaction most times. So physics and chemistry both deal with matter, as does biology and earth sciences, but chemistry in particular is the science of change, the changes matter undergoes and the energy that accompanies those changes. Keeping in the philosophical end of things, we have Sir Francis Bacon, a philosopher, really the natural philosopher that started science on his way. He dreamed that science would solve the world's problems, enrich human life with new inventions, and increase happiness and prosperity. And in some ways, his dreams have come true. We've done those things. Unfortunately, we've also created a whole host of problems. Chemists in particular have a lot to answer to. Onondaga Lake, just about 70 miles north of Binghamton, is one of the most polluted waterways in the world, and a lot of that is due to chemical industry, dumping chemical waste right into the lake, and really doing quite a bit of environmental damage there. Unfortunately, or fortunately, it was chemists that did the dirty deeds back in the day, and it's going to be chemists that clean it up. So we can't be afraid of chemists and chemicals, because yes, we do cause problems, but we're also the ones equipped to solve those problems. And hopefully after this course, you'll be equipped to think like a chemist and solve some chemical problems yourselves. And so now we've talked about a philosopher. Let's talk about one of our fellow scientists, Rachel Carson, a biologist, an environmental biologist, who published the groundbreaking work Silent Spring in 1962. And that really, as our image there shows, it's the classic that launched the environmental movement. Carson's Silent Spring talked about the use of chemicals to control insects, DDT in particular, as an insecticide that was making its way up the food chain, and really almost cost us our national emblem, the bald eagle. The eggshells were so thin that the eaglets weren't going to term, weren't able to survive. And by banning DDT, we've been very successful in reclaiming the bald eagle and other animals that were threatened to extinction because of the really irresponsible use of chemicals, using them without a whole lot of data, long-term studies, understanding how they would affect plant and animal life. And so hopefully, as a result of Rachel Carson's work and the work of others and the environmental movement that she launched, we will not be so glib about what we use in the future, and we'll continue to evaluate what's really necessary and what the outcomes are, good and bad, before we get ourselves into another situation like Carson described. So if you can't tell, I'm already a fan of green and sustainable chemistry. Green chemistry uses materials and processes that are intended to prevent or reduce pollution at its source. So green chemistry would be interested in taking things like styrofoam cups that are pretty ubiquitous. They're almost everywhere now, and replace them with something that's not quite so long-lived, not quite so difficult to decompose, not quite so toxic to make in the first place. Things like polylactides or other natural products, so things that we can get from plant sources instead of petroleum sources. Very similar idea, sustainable chemistry, we see is designed to meet the needs of the present generation without compromising the needs of future generations. So it goes hand in hand with green chemistry and that sustainability idea that hopefully you've heard elsewhere. Just gets at the heart of using things wisely, being good stewards of the earth, making sure that we're not using more than our share so that future generations will have resources as well. Just like we had these resources, we want to pass on a world of resources. And as we'll learn, chemistry and the atoms themselves are the ultimate in recycling. We can reuse those atoms again and again and again, and we'll see green chemistry and sustainable chemistry concepts come up throughout the rest of the course. So back to the basic idea of science. Again, if you like a more broad and easier to remember definition, we said logical argument based on empirical data, subject to skeptical review. Well, our text gives us 5 characteristics, and they're correct. Science is testable. That's that whole idea of empirical data. Reproducible, you don't just test once, you test multiple times. Explanatory, you can use logical explanations to discuss that testable and reproducible data. Predictive, you can make trends and be able to predict things in the future that you haven't yet discovered. When we talk about Mendeleev's table and ecosilicon and other things, that elements in particular that he was able to predict properties of based on the known properties of the known elements, that certainly gets at that idea. And finally, what might concern a lot of you is science is tentative. We cannot prove things to be true. We can only prove things to be false. So that's an unsettling thing for people who view scientists as decisive people who discover new things every day. Well, we are and we do, but we also are subject to change. We have to revise theories, for instance, when new evidence is discovered. So don't forget that very troubling, tentative characteristic of science. So those scientific hypotheses that you probably learned about in late elementary, middle school era are testable explanations of observed data. These hypotheses are tested by designing and performing experiments. And again, hopefully the experiments will be further tested and refined. It's very rare that we set out to prove something and we prove it and that's it. Most of the time in science, we set out to find something or to prove something, and instead we find something very different or don't prove what we expect. And that's where the major discoveries happen. We don't just give up, hopefully. We try to find out why the experiment went the way it did, why we got the data we got, and use that information to understand more about the natural world. Scientific laws and then scientific theories, as we'll talk about shortly, these are different than laws and theories in the legal sense. So a scientific law is a summary of large amounts of data and it provides descriptions of natural phenomena that have been reviewed usually by multiple scientists over multiple experiments. For example, we have the law of gravity, the law of conservation of mass or matter, etc. So in the physical sciences, that would be physics and chemistry, we tend to have our laws as mathematical formulae, like we see Boyle's law there, PV equals K, pressure times volume equals some constant. And as we'll see, PV equals nRT is an extension of that we'll get to in Chapter 6. In other sciences like biology, they might have the law of natural selection. They don't have a pithy little equation that they can do, but again, it's a fairly succinct idea that they've been able to refine over many experiments and lots of data analysis. So again, a scientific law. Here in chemistry, it's usually going to involve an equation for us. So the math fans will be happy when we get to some of these laws, and hopefully the non-math fans will become math fans very quickly. Now here's where we tend to have more trouble, and that's scientific theory. When people talk about theories in everyday speak, they often will have crackpot theories or conspiracy theories where there's not a whole lot of substance to it. That doesn't fly in science. If we have a scientific theory, it's a set of tested hypotheses that explain natural phenomena. Again, scientific theories are the best current explanation for natural phenomena. They're always tentative, and they may change as observations of nature change, but they don't become laws. A theory is different. It's broader than a law. So if you have the biological example I gave in the previous slide, we had the law of natural selection. That's part of the theory of evolution. So the theory is much broader. The theory is more philosophical. The laws tend to be more technical or mathematical, as we see. But again, they're different types of thing. A law won't become a theory in science. A theory won't become a law in science. They're different components. The laws tend to make up the theories, and the more evidence, the more laws that support a theory, like atomic theory. We have the law of definite proportions. We have the law of conservation of matter, and various other strengthening laws that help that theory. Atomic theory has been in use for hundreds of years and is probably a pretty good explanation, but it could be refined if we discover something new and different tomorrow. We're probably not going to abandon the atom, but we may have to change the way we think about it, as we have over the years already. And again, scientists, we like to use mathematical formulae and other ways of understanding, but a great way to begin in science is to have scientific models, tangible items or pictures used to represent invisible processes. We've been talking already about atoms. Our next chapter is all about atoms, but atoms are invisible. We can't see them directly. It's not that we don't have powerful enough microscope. Certain types of microscopes exist that can visualize atoms, but then if you believe that, you've got to believe in electrons, and so we've got to have again a little bit of a model, a way to picture something that's not quite perfect, but it gets us at the understanding that we need. So we see here in this image some spheres that are meant to represent water molecules or air molecules. Again, they don't really look like that. The water molecule has more of a Mickey Mouse look to it, and it's very small. But for the purposes of this model, it's a good, quick description where we can clearly tell that the water molecules are the blue spheres and the air molecules are the white spheres. Understanding that neither one is probably spherical. The water molecule, again, has more of that Mickey Mouse shape. Nitrogen or oxygen molecules are going to be a little more linear than spherical, but the model's still good, and it still holds, and it gets us at some understanding in a way that's convenient and easy. Trying to get all the details right, especially at this stage, is too much for the beginning student. So we've got to accept some imperfections and have some models that don't hold 100% but get us where we need to be. So we're in our introduction, and we've already touched on atoms and molecules and modeling, so we might as well just talk a little bit about molecular modeling. So first, we've got to explain what a molecule is. So molecules are groups of two or more atoms held together by chemical bonds. So again, in our last example, we were treating them all as spheres. Atoms would be spherical, but molecules tend not to be spherical, although a model could show them spherical. Molecular models are three-dimensional representations of molecules, and usually we try to get a little better, closer to reality than that last image. But again, we're not trying to overburden people at this stage. You'll learn more and more throughout the course of this course, and hopefully you'll get excited enough about chemistry that you'll want to take further courses where you'll learn more details and discover, unfortunately, that I've had to oversimplify things. I hate to say lie to you, but I've had to oversimplify things to keep it appropriate. And I'd love to have you come back and tell me when you learn all the very rigorous math and physics that get you a little closer to reality, because you could instruct me probably by then. One of the great illusions of science is that we can do anything. People think scientists are superhuman. We just can do it all. We know it all. And although that's very flattering, and some scientists would like that lie to go on, it's just not true. And the sooner we recognize the limitations of science, the more scientific we can be about things. So as our text tells us, science is limited to studying that which is observable, as well as processes in which variables can be controlled. So in designing experiments, we want to observe only one change at a time. We want to try to control everything else so that we really can understand how that change alone impacts the process. This is very difficult to do, and some things are just impossible. The experiments just cannot be designed now, or possibly even in the future, to accomplish things like that. The race for absolute zero is an example of something that might never be approached. We might never be able to get right there to absolute zero, but it's not stopping scientists from trying. We have the idea of observing. By observing a system, we influence it. And that's unsettling to scientists, but it's true. So we have to be very careful about the limitations inherent in science, and the limitations, especially as we go to the very, very small. The world at the nanoscale and smaller doesn't work like the world we're used to, and we see some limitations as we get into things like the idea of trying to know the location and momentum of an electron. It's just not possible to know both with a lot of precision. So these things are just features of science that you may not have been aware of before, but now that you know, science has done a lot of great things and will continue to improve our lives, but there are some limitations to it. All right, so more of a risk management approach to things. Let's talk about science and technologies, the risks and benefits. So science and technology are interrelated. We already talked about the technology being the more mathematical, experimental end of science, which also has that philosophical bend to it. And they both involve risks and benefits. So we can use a desirability quotient, abbreviated DQ here, to compare the risks to the benefits, or benefits to the risks as we have it here. So we would just estimate what benefit we expect divided by the risk, and we'll get that desirability quotient. Obviously, we want as much benefit as possible with as little risk as possible, so we're hoping for a DQ that's a very large number. So if we look at table 1.1 from our text, rather grim approximate lifetime risks of death in the United States. Again, I say grim because the lifetime risk is 1 from all causes. All of us will die of some cause at some point. But then if we're looking at other risks, cigarettes, a 0.25 risk, that's a 1 in 4 approximate lifetime odds. That's pretty high. So we would prefer not to smoke or to cease smoking if we're already smokers, because that's a pretty significant lifetime risk. If we go down to something like airplane accidents or terrorist attacks, again, these are horrible things, and they do happen. Unfortunately, they happen very often in our world. But still, as an overall lifetime risk, they're quite unlikely to occur. Again, depending on the details. So if we're talking about something like an airplane crash, that's about a 1 in 20,000 lifetime odd, whereas a terrorist attack, it's going to depend on how frequently those happen, right? It'd be 1 in 1,300 if we get something like the 9/11 level terrorist attack every year. Fortunately, we don't, so maybe 1 in 13,000 is a little better estimate if we say something of that magnitude every 10 years. Hopefully even less frequently than that. But again, the purpose of the table is to show us that there are certain activities or things that we might do that are more likely to increase our risk, and there are other things that we have relatively little control over, but again, they do tend to have fairly low risks. Chemistry is often called the central science, and as I've already said, probably most of you are not here to be chemists, and that's okay. I'd love everyone to be a chemist, but it would be a fairly boring world if we all became chemists. It'll be great for us for a little while, and then we'd miss all those other things that other professions contribute. So we see here chemistry being the central science. We're really important to a lot of things that a lot of other sciences and allied health fields do. We're important to agriculture and botany and archaeology and meteorology, and a lot of you are probably in the course because you're interested in dentistry or medicine. So those are also very important fields that rely heavily on chemistry. So we tend to have pretty good opinions of ourselves because as chemists we tend to be pretty useful people since chemistry is involved in so many different aspects of life. Okay, so talking about some problems and solving problems using science, not necessarily just chemistry, but science in general. We have what's known as applied research, and applied research involves studying a specific problem in industry or the environment and looking for a specific solution. It's a relatively lower risk than what we'd call pure research or basic research, but it tends to be where we put most of our emphasis nowadays. The National Science Foundation and the National Institutes of Health, these huge government funded agencies tend to support research that's more applied in nature because we have problems that we want solved, and it's important to get those solutions. You don't get huge breakthroughs usually this way, but you do get little incremental improvements, and that's what most people are after anyway. If we continue on the slide, they're talking about George Washington Carver's work with peanuts as an example of the applied research that we just discussed. And from the peanut, he developed more than 300 products. And peanuts are plentiful in our country. They grow very well in certain regions, and so that was great research that we still use today. Peanut butter and other inventions, discoveries that George Washington Carver made. But again, it's nice if you like peanuts, but if you have a peanut allergy, you're probably not going to be a fan of too much of George Washington Carver's work. So if we contrast that applied research that we just talked about with basic research, or pure research I called it previously, This involves the search for knowledge for its own sake. This is very philosophical, and we tend not to, unfortunately, fund a whole lot of this anymore in the United States. We tend to want an answer to a problem here, and if we're going to spend taxpayers' money, we want something that's got a pretty good likelihood of success, and that's applied research. Basic research, you get these fundamental understandings, and again, as the slide goes on, the findings of basic research may someday be applied to a specific problem in industry or the environment, but it's not being researched at that depth at this point for that specific outcome. The basic research is just to get fundamental understandings, and then those fundamental understandings can drastically change the way that we think about a particular branch of science, and we might have a whole host of applications that we might be able to get out of that pure basic research, but we don't go in with the application in mind. We're not necessarily thinking of the outcomes that we can have. We're just trying to think about the problem and find out more about that area. So Gertrude Ellion's work with purines and their role in the cell is an example of basic research. She just wanted to know more about these purines and what they're doing and why they're important. And from that, she was able to discover a lot of fundamental important science about the cell through her basic research. So we've gotten a little far afield here, so let's pull it back in, draw it back in to chemistry. So this is a chemistry class, fundamental chemistry, and as we've said previously, it's the study of matter and its changes and the energy that accompanies those changes. But I guess we should go back and define matter, and as you may recall from middle school, matter is anything that has mass and also has volume. That's a very vague description, but it's the only one that's really scientifically accurate. So matter is stuff, if you want something that's a little less scientific sounding. It has mass and it takes up space. So mass and weight tend to be a problem, especially for those of us in the U.S. Mass is the measure of the amount of matter in an object, and weight is the measure of the gravitational force on the matter in the object. So mass has certain units, the kilogram being the fundamental unit, and you may know your mass in kilograms. It's interesting that the U.S. Being so obsessed with weight, we do still use pounds, which is a weight example. It's a force. You'd think we might be compelled to go with kilograms like the rest of the world, which is actually mass, not weight. But it would be about half. Your body weight in pounds would be your body mass in kilograms. So again, they are slightly different because a mass is the amount of matter in the object. Weight is a force acting on that object. But still, we often use them interchangeably, and your mass would be about half your weight. Your mass in kilograms would be about half your weight in pounds. So if we go a little deeper, mass and weight that we just discussed, which are distinct, and we should keep them distinct in this course, even if, when you go to the doctor's office, they tell you your mass in kilograms, they misspeak and say it's weight or something. We'll let that go out in the real world, but here in the class, we'll keep it all distinct. So mass and weight are both examples, along with color, of what we call physical properties, properties of a substance that can be observed without changing the substance. So we're not undergoing any chemical change. We're just looking at the substance, its color, its mass, its weight, for example. These are things that would be called physical properties. Density would be another one. A certain substance has a fixed density, whether you have just a little of it or a whole bunch of it. If it's just that one substance, it has that characteristic density. And here, if we look at table 1.2 from the text, there's a number of other physical properties. So we already had mass and color. Also weight was on the previous slide, and I have already mentioned density. But there's other properties like temperature, which often gets us into boiling points or melting points. We have taste or odor, which can be characteristic of certain substances. Many substances have no taste or odor, but others have very characteristic tastes and odors, for example. And then hardness. We have diamond, which is the hardest known material in 3 dimensions. And contrast that with something like sodium metal, which is very soft. So these are examples of physical properties. Chemical properties, on the other hand, are properties of a substance that can only be studied by forming new substances, by undergoing chemical change, chemical reaction. So for instance, if we look at table 1.3 from the text, a substance like iron has the chemical property that it rusts. And again, when we say rust, there's lots of examples. Most metals will rust in some way. But when we talk about iron, we're talking about forming a very specific rust, combining with oxygen to form iron oxide that has that characteristic reddish color. Now that sort of red-brown rusty color is really iron 3 oxide. Carbon will burn, so it can combine with oxygen, but it doesn't rust in the same way that iron rusts, because the carbon dioxide that it forms is also a gas, whereas the iron oxide that iron forms is a solid. Silver tarnishes. It combines with sulfur to form silver sulfide, or oxygen to form silver oxide. We have nitroglycerin is explosive. It'll decompose to produce a mixture of gases, and if that's done quickly and with much heat, that's a very dangerous scenario. Carbon monoxide is toxic because of what it does with our hemoglobin. It binds a lot more tightly to that hemoglobin than oxygen does. So oxygen binds loosely, which sounds bad, but when you think that oxygen needs to be released later, that's a good thing. The carbon monoxide binds so tightly that it doesn't release, and so it stays bound to the hemoglobin. And once you've inhaled enough carbon monoxide to max out your hemoglobin sites, it's unfortunately a very fatal scenario. That's why we have carbon monoxide detectors and alarms to let us know if there's this unsafe, odorless, colorless gas that's very, very toxic to humans. Finally, neon, its chemical property is that it doesn't do much chemistry. It's inert. It doesn't react with anything so far that we've been able to force it to. So we'll talk about neon and the other so-called noble gases later on in the course. Alright, so we've talked about physical and chemical properties. Now let's talk about physical changes. Physical changes are changes in which the chemical identity of the substance is not changed. So that seems funny to say that they're changed where something's not changed. Well, the physical state can be changed. So examples here would be melting or freezing. So if we take liquid water and we freeze it to solid ice, we didn't change the water at the molecular level. It's still H2O, and we can melt it again, take that solid ice and heat it, melt it back to the liquid. So we haven't changed the chemical compound, we've just changed the physical layout from the very structured frozen ice to the much more free-flowing liquid water, and then if we continued heating to the very, very random and far away molecules in the gas phase of water vapor. So physical changes, we change the physical layout, usually how close things are and how rigid the structure is, and we haven't changed the chemical bonding at all. So that description of physical change and using phase changes leads us right into our classification of matter. So a solid has a definite shape and volume. An ice cube, for instance, has a very fixed shape and volume, and that's quite clear. A liquid still has the definite volume. You can't compress it a lot, but it doesn't really have a definite shape. It'll flow and take the shape of whatever container it's in. If you put a couple ice cubes in a cup, they're still going to look like ice cubes. But if you pour liquid water in the cup, the liquid water will take the shape of the cup. Finally, a gas has neither definite volume nor definite shape. So a water vapor would occupy the entire volume of the liquid cup and would just take the shape of the container that it's in. And now we're back to those models, those little spheres to represent elements or compounds. So here if we have a solid, we notice that the pattern is very regular. It's a very fixed layout, and that's what gives rise to that rigid shape and the fixed volume. If we look over to the liquid, now we have very close together particles, just like in the solid, but they're not as rigid. They're not as fixed in how they are laid out. They can flow across each other and therefore take the shape of the container. Finally, the gas, we see they're much further apart, and this particular image doesn't even do it justice, because ordinarily gases are much further apart even than this would show. So they're far apart, which allows them to fill the whole volume of a container, and they can flow, so they'll take the shape of their container as well. We see here a nice graphic organizer, a way to take matter, our big idea, and to segregate it into different types. So we see that we have all matter can be classified as either substances on our left or mixtures on our right. So the pure substances would either be elements or compounds, where the entire sample is the same thing throughout, whether that's gold, like our gold coin, or whether that's water molecules, like our glass of water. Well, that would steer us in the direction of elements, which we only have about 118 of those to date, or compounds, which we have many, many billions of to consider. If we go the other direction for all matter, instead of talking about pure substances, which are relatively rare, if we look at mixtures, mixtures tend to be how we encounter things in the natural world. There are some things like gold and lead, elements that occur as elements in the natural world, and lots of compounds like sodium chloride, etc. But they tend to be parts of mixtures. And when we consider mixtures, we have also two groupings. There's homogeneous, where the mixture looks the same throughout. So if we look here, we might have a wedding band that's say 18 karat gold. So there's mostly gold atoms, but there's some silver atoms mixed in, for instance. Or we might have something that's heterogeneous. We can tell just by looking at it that it's different, and what we see on that plate is some I think iron filings and some sulfur filings, or maybe some water, I guess, and sulfur, where we can see very clearly that the sulfur particles are distinct, and the water, you can pick the sulfur out of the water very easily. So there we have our groupings of matter into either pure substances that look the same throughout, and they're either elements or compounds, or we have mixtures that either look the same throughout, as we have our solid mixture there, solid solution of gold and silver atoms, for instance, or we have our very obvious mixture that has distinct particles in it. Alright, so going a little deeper into the idea of elements from our graphic organizer, elements are composed of only one type of atom, and the atom, from the Greek, the alpha privative meaning without or not, and then tome, meaning to cut, that which cannot be cut. Of course, nowadays we can cut the atom, or split the atom as it's more commonly called. But once we do that, we don't have the same properties of that element. So the atom is the smallest component of the element that retains the properties of the element. So it's still an important idea, even if its name is a little off. So atoms are the smallest particle of an element, and elements are represented by their chemical symbols. So for example, we have Cl for chlorine, H for hydrogen, Mg for magnesium. So when we use those, we're not typically talking about just a single atom, but that's the smallest unit that would be able to distinguish magnesium from chlorine or from hydrogen, for instance. Once we split it into smaller portions, then we just have what we call the subatomic particles, and those are not distinguishing for particular elements. So if you remember a few slides ago, we had either pure substances being elements or compounds. So now compounds are made of two or more elements chemically combined. And so many compounds exist as groups of atoms bonded together as a unit. These units are called molecules. And so we tend to use molecule to mean pretty well everything. That's not always the case. When you have something like sodium chloride, we should actually call that a formula unit, because salts are not molecular, but rather charged ions. So again, sodium chloride is a compound because it has two different elements, sodium and chloride ions, but they're not technically molecules like something like carbon dioxide would be, where it's carbon chemically bonded in a molecular fashion to oxygen. And so if we went the other way, instead of pure substances, the other way to classify matter, the other way that matter occurs, would be as mixtures. So a mixture is a physical blend of two or more substances. And the key there is physical, because we can physically separate it. Homogeneous mixtures are uniform in composition. So if you think about table sugar that you dissolve in water, it looks the same as pure water, but obviously it tastes quite a bit different. If you wanted to get that table sugar back from the water, you could boil off all the water, and then you'd have the table sugar left if you're careful about it. If you do it at a low enough temperature that you don't end up with caramel or charred sugar at the end. In contrast, we had our heterogeneous mixture. They're not uniform in composition. You can see that the heterogeneous mixture in that slide had little pieces in the water that could easily be picked out, just physically separated, because they were already obviously different. So homogeneous mixtures we also can call solutions, because they look the same throughout. Heterogeneous mixtures are clearly different, and you can pick out the different pieces oftentimes, if they're large differences, just by picking out the different particles. So now that we've talked about the ways matter occurs, let's talk about some fundamental measurements we can make of matter. So you see there's the 7 SI, Système International, the International System, base units. So for length, the base unit is the meter, which we spell M-E-T-E-R. The rest of the world usually M-E-T-R-E is the way it's spelled, but that's how we do it in the States, and we usually don't worry much about how the rest of the world does it. The symbol of that unit is lowercase m. So here in the States, we typically use feet anyway, but in the sciences at least, scientists have agreed on these units, and so we use meter, and we feel very much at home anywhere in the world, because we use the meter like the rest of the world does. We just don't spell it the way they do. Scientists also recognize mass, the fundamental unit for mass, as the kilogram. Again, it's not the plain old gram, because that's just too small. Kilogram tends to be the right amount for most of the things that we would tend to be concerned with. Especially, we talked previously about mass versus body weight, and so kilograms would be appropriate for that. So if you want to get your mind around what a kilogram is, well, you take your body weight in pounds and divide it by 2.2, and you'll get your body mass in kilograms. Time has the second as its fundamental unit, and the lowercase s as the abbreviation. Temperature, the base scale, is the Kelvin scale, capital K. We tend to use Fahrenheit here in the United States, but the rest of the world tends to use degrees Celsius. Again, neither of those is accepted as the base unit. In science, it's the Kelvin unit, capital K. The amount of substance, that's the mole. That's the one that belongs to the chemists. A lot of these other ones the physicists would try to claim, but the chemist is ours. So we love the mole, and that's why we didn't abbreviate it much. The abbreviation, we just use that E at the end to have MOL. Electric current, the fundamental unit is the ampere, and its symbol is a capital A. And then luminous intensity is measured in candela, and CD lowercase would be the unit abbreviation. So from those base units, we can get much larger and much smaller, and that tends to be done with prefixes. And the reason scientists love the metric system, and why we tend to use it, even though in the everyday U.S. Usage, they use bizarre Fahrenheit and feet and all this. We recognize the utility of this metric unit based on the powers of 10. So you can see we're into terabytes and gigabytes in computing. So those are very large number, tera being 10 to the 12, giga 10 to the 9, mega. I was around when storage devices were megabytes or even kilobytes. So a number of you may not recall those days, but some of us are old enough to remember those. Hecto, deca, we don't use very much, but those are the appropriate. For 10 to the 1 is deca, and 10 to the 2 is hecto. In chemistry, we tend to go very small, so deci, centi, milli, micro, nano, those tend to be where we tend to focus. When you get much smaller, like pico or femto, that could be subatomic particles or very short times. Femtoseconds might talk about certain transitions in chemistry. So for our course, we tend to be between that 10 to the minus 9, nanotechnology is a big phrase these days, up to the deci, tend to be the realm of the chemists. So if we look at measurement of matter, we have mass. The SI base unit of mass is the kilogram. And so if we have a lab scale quantity of something, it tends to be in the kilogram range. Length, the SI base unit of length is the meter. So in the lab, we tend to have millimeters or centimeters. We don't often work with things that are meter long, but we might. Volume, the SI base unit is the cubic meter. Again, this is not a fundamental unit, right? Because volume is length, width, and height. So that's why we have the meter cubed when we multiply those three dimensions. And then finally, time, the SI base unit of time is the second. And obviously, time is a very important variable in most chemical reactions. As we mentioned just moments ago, nanotechnology, the nano world, we have lots and lots of hopes pinned on nano, and so far we've had a few successes, right? We have pants that you don't have to iron because of nanotechnology; they don't get stained as easily. But this is pretty small potatoes compared to what we're hoping for, and hopefully it's not just hype in nanotechnology. We've got a lot of hopes for very efficient technologies, low energy usage, all sorts of really, really interesting things that are just around the corner based on nanotechnology, which is the study of manipulating matter at the atomic or molecular level. So using things like molecular size wires, you can do electronic processes that would have been impossible using traditional wires, even very thin metal wires. For the conventional electronics, these nano electronics are going to be very, very exciting once they get to the end user stage. And so now we'll shift gears a bit and talk a little about density. So we talked about ideas of mass and volume previously. Density is that ratio of mass to volume. So it's the amount of matter that fits in a given amount of space. So if we think about the example they give here on the slide, the density of copper is 8.94 grams per cubic centimeter. So those copper atoms are packed in pretty tightly, and you're able to get quite a lot of mass in a given amount of volume. As you probably recall, the density of water at roughly room temperature is about 1.00 grams per cubic centimeter. So those water molecules are not tightly packed. They don't weigh as much to begin with as the copper atoms, and so we have to consider that, the mass of the matter and the amount of space that it takes up. Mercury is considerably more dense than copper. So if we want to do a little practice, you do have those Mastering Chemistry homework sets to work on, so they'll give you lots more practice, and you shouldn't wait until the due date. They tend to take at least an hour and a half, and that's if you know everything you're doing from the beginning, and most of us aren't that lucky. So hopefully after this lecture you'll go ahead and try the first several questions. All have to do with Chapter 1. Anything that you recognize, you should go ahead and work on and try, and get in touch with me if you're having trouble. But before we go into Mastering Chemistry mode, let's practice together how we would calculate the density of a metal sample with a mass of 18.96 grams and a volume of 4.31 cubic centimeters. Using the density formula, density equals mass over volume. We were very kind here. You're given the mass, you're given the volume, so it's just plug and chug math. So if we plug in that 18.96 grams and divide it by the 4.31 cubic centimeters, we have our result of 4.40 grams per cubic centimeter for the density of that metal sample. Notice that the units are important. We didn't cancel units, and we shouldn't. Density should have a mass unit per volume unit, and typically that mass per volume unit is grams per cubic centimeters, or grams per milliliter if we're dealing with liquids. A milliliter is equal to 1 cubic centimeter. Alright, and so discussing another one of our objectives, contrasting heat and temperature. We have to first understand energy, and here's another one of those vague definitions, right? Matter is anything that has mass and takes up space. Energy is the ability to change matter either physically or chemically. So nice and vague, but again, if we want to be always correct, we've got to keep it pretty abstract. Energy exists in two major forms. We have potential energy, is stored energy, and kinetic energy, which is energy in motion. Heat is energy that's transferred from hotter objects to cooler objects, and temperature is the average kinetic energy of the atoms or molecules that make up an object. So if we take a hot object and we submerge it in a cool object, like if we heated up a block of metal and then put it into cold water, well, we'd have the very quickly vibrating metal atoms causing the relatively slower moving water molecules to speed up, and so we'd end up with something at the end that's a little higher temperature for the water and a lower temperature for the metal, because there would be that transfer of heat. The hotter object transfers some of that molecular motion to the cooler objects. So the cooler object heats up a little, the hotter object cools down, and we get an overall temperature that's somewhere between the temperature of the hot object and the temperature of the cool object, depending on how much hot object versus cool object we had. So for our units of heat, heat energy is often measured in calories here in the US or joules everywhere else. 1 calorie is the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. So if you want to know the conversion, because you go anywhere else, if we're headed to Brazil for the Summer Olympics, which was during their winter, strangely enough, you would need to know that 1 calorie is equal to 4.184 joules, because you're going to find food not listed in calories, but rather in joules for energy content. Even if you choose to stay here in the United States and never set foot anywhere else, you'll also need to know that a food calorie, which is a capital CAL calorie, is actually a kilocalorie for a lowercase CAL calorie. So those food objects that you'll look at the nutritional information and see a calorie count, those are food calories and should be a capital C, because they are 1,000 times the little c calories. So based on just the amount of energy stored, it's convenient to have it as a capital C food calorie, because you're going to be able to heat a lot more water with the calories released from food than you would with something that we might be studying here in the course. So notice that food calorie would be, instead of 4.184 joules per regular lowercase c calorie, you get 4,184 joules out of a capital C calorie, a food calorie. All right, and we'll end the chapter out thinking about the different temperature scales. So here in the US, we tend to use the Fahrenheit scale, and it's a fairly bizarre scale, but it's the one we're used to. We know that 32 degrees Fahrenheit is the freezing point of water, 98.2 is average body temperature, 212 Fahrenheit would be the boiling point of water, and absolute zero, if we could indeed reach it, would be about negative 460 Fahrenheit. Contrast that with the Celsius and Kelvin scales. We have those right next to each other because they're at least a little easier to relate, because a Celsius degree is equal to a Kelvin unit. So we see they're not the same values. Boiling water would happen at 1 atmosphere of pressure at about 100 degrees Celsius and 373 Kelvin. So they're different, obviously. But if we look at the freezing point of water to the boiling point of water, that's 100 Celsius degrees. It's also 100 Kelvin units, right? 273 Kelvin for the freezing point of water to 373 Kelvin for the boiling point of water. So the magnitude of the scales is equal. The numbers are just offset by 273, right? 0 Celsius is 273 Kelvin. So why do we need this other scale if the Celsius and Kelvin temperature values are equal in magnitude? Well, it's because the Kelvin scale is an absolute temperature scale. So 0 is 0, no molecular motion. And actually that's not even true, because we were off a bit, and so you can get a little below 0, but it's not something that we tend to talk about here in a course like this. So when we correct it, 0 would be 0, no molecular motion, and we've come within 0.000 or so Kelvin, but we haven't hit what would truly be absolute 0, where all molecular motion stops. So for simplicity's sake, we tend to convert between Celsius and Kelvin here in the course. It's a lot easier, more straightforward than dealing with that Fahrenheit nonsense. So to convert from Celsius to Kelvin, we need to add the 273.15. That's where I talked about that little difference from where we really thought we were with the Kelvin scale. So if you're given a Celsius temperature and you want to convert it to a Kelvin temperature, you need to add 273.15 to make up for the offset between 0 Celsius and 0 Kelvin. So if we're looking at that human body temperature, which is roughly 37 degrees Celsius for the average person, to convert that into Kelvin units, we would take that 37, the Celsius value, and we'd add the 273.15 to get a 310 Kelvin, or 310.15 if you're being very careful. We'll talk about why we stopped at 310 Kelvin when we talk about significant figures. So if you've made it through all of this, congratulations. You've been able to listen to me for more than an hour and not fall asleep. Let's just round things out by talking about critical thinking and validity. So we talked about scientists as being people who study phenomena using empirical data, logical argument, and skeptical review. So let's talk a little bit about being skeptical. You can test the validity of a claim by using the Flair's test, is how our textbook provides it. So F for falsifiability, L for logic, R for replicability, and S for sufficiency. If a claim passes all 4 Flair's tests, then it may be true, though it still can be proven false. If it fails even one of the tests, it is likely to be false. So again, we have to be careful in science. We don't prove things to be true, we prove things to be false. So using these 4 features, we can take a particular claim. You're bombarded by claims all the time in advertising, and determine whether or not they would be expected to be true or expected to be false. Again, the more of these tests that are failed, the more likely something is to be false. Alright, so we've finished chapter 1, and hopefully you're in a position to go and get right to your Mastering Chemistry homework on it, and hopefully have no problems whatsoever. Go back to your text to get in touch with me if you are stumbled by any of those questions. Alright, good luck, chemists.